Percent yield, a Dr. Kelly reaction, taking stoichiometry to the next level. If you haven't met percent yield, you're about to, and believe me, the results are good. Matter of fact, if you want a high percentage, continue listening. Alright, the best way to understand percent yield in laboratory chemistry is to actually step out of the lab and step into a situation that's a little bit more touchable and relatable for us. We work at a car factory, and in our car factory we make big red cars, and those big red cars have 4 wheels and 2 doors because I like sports cars. So, to make a car, it takes 4 wheels and 2 doors. When I take my inventory, in my factory, I have 120 wheels and 80 doors. How many cars can I make? Alright, yeah, I know. A lot of you are already shouting out the answer to me. That's awesome! You're going to have no trouble if you're already shouting out the answer. However, how did you get that answer? No. Hey, wait a second. That was one of those, what do they call it? Rhetorical questions, right? I actually want to tell you how you got the answer, even though I know how you got the answer, because I want to highlight the thought process you went through to get that answer. Whether you realize it or not, to answer that question, you worked a series of 2 smaller questions. You said, how many cars can I make with 120 wheels? And to answer that question, you actually use that stoichiometry method we've been using since the beginning of chemistry class, where we said, okay, I've got 120 wheels. I don't want wheels, so I'm going to place them where they cancel out. And according to my chemical equation, for every 4 wheels I have, I can produce 1 car. So if I multiply everything on top and divide through everything on the bottom, it turns out I can make 30 cars with my 120 wheels. That was the first question you asked yourself. The next question you asked yourself was, how many cars can I make with 80 doors? Well, I've got 80 doors, and I know according to my chemical equation it takes 2 doors to make 1 car. I multiply everything on top, divide through by everything on the bottom. So I have enough doors to make 40 cars. So let's see. I have enough doors to make 40 cars. I have enough wheels to make 30 cars. So I can obviously make 70 cars, right? The correct answer to that question was no. I can't make 70 cars, can I? How many cars can I actually make? I can only make 30 cars, right? I can only make the lesser of the 2 amounts. If I was in lab, I would call this lesser amount that I can make my theoretical yield. When carrying out these calculations, my theoretical yield will always be the smaller number. Despite the fact that it's the smaller number, the theoretical yield represents the amount of product I should generate in theory. I should produce in theory. So my theoretical yield represents the amount of product I should produce in theory. And it's always going to be the lesser of two numbers. It's always going to be the lesser amount when you're comparing the yields between two competing reagents. So what limited my production of cars? What of my two reagents was completely consumed? So which of my two reactants was completely consumed in my car production? It was my 120 wheels, right? My 120 wheels limited the amount of cars I could produce. It's what determined the number of cars I could produce. Therefore, I refer to this 120 cars that limited, my 120 wheels that limited my production are what are known as my limiting reagent. And the limiting reagent is whatever produces, let me phrase that a little bit better even. My limiting reagent is my reactant that produces the smaller amount and limits my production of product. You'll also see the limiting reagent defined in several textbooks as the reagent that's consumed first, but let's just say I'm not at equilibrium with that definition. But it's the reagent that limits my production. So in this example, my 120 wheels would be my limiting reagent. Now, back to my car factory. In my car factory, I have enough parts to make 30 cars. Well, I crank up my car factory, and at the end of the day, and I go until I run out of parts. When I count the number of cars I made, I start my car factory and go until I run out of parts. When I count the number of cars I made, I discover that I produced only 25 cars. So wait a second. I had enough parts to produce 30 cars, right? In theory, I should have been able to produce 30 cars. But for some reason, when I ran my factory, I only produced 25 cars. This 25 cars would be referred to as my actual yield. Remember, those of you who've ever had a lab class at any time in your experience, you often know that sometimes the chemicals forget to read the lab instructions, yes? Not only that, but in a chemical process, particularly one where you're synthesizing a compound, you're often trading product for purity, or purity for product. In other words, when I perform a lab, I may purposely wind up losing some of my product in order to ensure that my product doesn't have any foreign substances in it. What you actually produce in the laboratory is referred to as your actual yield. The actual yield is the actual amount produced in the laboratory. Is this a lab class, by the way? No, it's not, right? This is a lecture class. Actually, this is a YouTube video that you're listening to. But I digress. Since this isn't a lab class, the only way you can get an actual yield in this class is if I tell you what the actual yield is. So a problem will always contain as a number an actual yield, and that may cause you some issues later on. But don't worry, we'll address those too. So your actual yield is 25 cars. In theory, I should have produced 30. Remember we said our theoretical yield was 30 cars. What happened to my missing 5 cars? Well, I don't know. I go and ask my new foreman, Tony Soprano, and when I ask him what happened to the 5 cars, he tells me I'm asking dangerous questions. Personally dangerous questions. And that unless I wanted to see my doctor, I probably shouldn't ask any further. So I have no idea what happened to my missing 5 cars. So if I wanted to grade the production of my factory, I could use a quantity known as percent yield. Percent yield is equal to the amount you actually produce, or in other words, your actual yield, divided by your theoretical yield. And because it's a percent, you're of course going to multiply by 100. So for our car factory, we actually produced 25 cars. In theory, we could have produced 30 cars. So our percent yield would be 83%. So that's what actual yield are, theoretical yield, percent yield, and limiting reagent are. All right, here's a very colorful summary of 2 of the terms that we met on the previous slide. Limiting reagent and theoretical yield. Theoretical yield is the amount of product a reaction should produce in theory. Limiting reagent is the reactant whose quantity limits the production of product. In other words, our limiting reagent is whatever produces the theoretical yield, or determines the theoretical yield. I would pause me and write these down if you're in my class. Matter of fact, if you're in my class, I strongly recommend that you pause me and write down these definitions. And as long as you're pausing me and writing things down, why don't you write down Neverwhere? Write down Neverwhere. Perhaps my favorite book of all times, Neverwhere. 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 One last quick term here, and that's the actual yield. Remember, the actual yield is the amount of product actually produced in the laboratory. In our case, our 25 cars. So that brings your terms up to snuff. Now let's bring us back into the world of the laboratory. All right, let's take a look at an actual chemical equation now in an actual laboratory experiment. How many grams of ammonia can I produce with 30 grams of nitrogen and 12 grams of hydrogen? When I performed the experiment in the lab, I produced 18.2 grams of ammonia. What is my percent yield? And I did that again, didn't I? I always misspell. There we go. Thank you very much. What is my percent yield? The first problem a lot of people have when addressing a problem like this is it looks like alphabet soup. I mean, my word, I have 3 different numbers. Most of the problems we've encountered in chemistry up till now always start with 1. So our first thing I want to do is I want to eliminate one of the numbers. They gave me an amount of product here. So that's a clue that they've given me an amount of product. Then as I read the sentence, they say that this was produced in the laboratory. Somebody actually produced this. That's my second clue. It was actually produced when an experiment was carried out. That lets me know that this 18.2 grams of ammonia is my actual yield. And that means I get to forget about this number until my last step. In other words, I need to listen to my foreman and forget about it. So I'm going to forget about it until the last step of the problem. It's dead to me. It doesn't exist until the last step of the problem. As a matter of fact, I've seen students go to the length of actually kind of drawing one line through it so that they're not tempted to use it. All right, so that leaves me now with 2 numbers in my problem. My amount of nitrogen and my amount of hydrogen. With our 2 numbers of product, we're in a situation analogous to our car situation again. Remember, we handled our car situation by asking ourselves 2 questions. We're going to handle our ammonia situation the exact same way by asking ourselves 2 questions. The first question we're going to ask ourselves is, how much ammonia can I produce with 30 grams of nitrogen? Then I'm going to ask myself, how much ammonia can I produce with 12 grams of hydrogen? Now, what I'm doing is I'm assuming that I have excess of the other reagent in both of these. Or I'm assuming that I have excess of the other reactant in both of these is another way of putting it. So I'm going to work my problem twice, just like I do with my cars. I'm going to say, okay, I have 30 grams of nitrogen. I don't want 30 grams of nitrogen. So I'm going to place grams of nitrogen where they cancel out. The only thing I ever know about grams is what my periodic chart tells me. And my periodic chart tells me that 1 mole of nitrogen is 14.007 grams. I have 2 moles of elemental nitrogen and 1 mole of molecular nitrogen. And that gives me 1 mole of diatomic nitrogen having a mass of 28.014 grams. So I've placed grams of nitrogen where they cancel out. And now I have moles of nitrogen. I don't want moles of nitrogen, so I place moles of nitrogen where they cancel out. I know the relationship between moles of nitrogen and moles of ammonia. For every 1 mole of nitrogen, I can produce 2 moles of ammonia. But I don't want moles of ammonia. I want grams of ammonia. So I'm going to place moles of ammonia where they cancel out. I always know the relationship between moles and grams because that's what the periodic table tells me. And 1 mole of ammonia has 14.007 grams of nitrogen and 3 times 1.008 grams of hydrogen for 17.031 grams of ammonia. I multiply everything on top, I divide through by everything on the bottom, and I wind up with, drum roll please, 30 divided by 28.014. Of course you were doing this with me at home, I am sure. And you get that you have enough ammonia to produce 36.5 grams of ammonia. You have enough nitrogen to produce 36.5 grams of ammonia. In other words, I have enough wheels to produce 36.5 cars. So how many cars can I produce with my doors here? So I'm going to work it again, but this time I'm going to start with my 12 grams of hydrogen. I have grams of hydrogen, I don't want them. So I'm going to place grams of hydrogen where they cancel out. I know according to my periodic table, 1 mole of hydrogen is 2.016 grams of hydrogen. I've gotten rid of grams of hydrogen. I have moles of hydrogen, but I don't want moles of hydrogen. So I'm going to place my moles of hydrogen where they cancel out. And according to my equation up here, for every 3 moles of hydrogen I have, I can get 2 moles of ammonia. So 3 moles of hydrogen, 2 moles of ammonia. And for every 1 mole of ammonia, I don't want moles of ammonia, I want grams of ammonia. For every 1 mole of ammonia, I know that it has a mass of 17.031, that's a 31 grams of ammonia. I multiply everything on top, divide through by everything on the bottom here. So 12 divided by 2.016, divide by 3 times 2 times 17.031, and I get that I have enough hydrogen to produce 67.6 grams of ammonia. So, I have enough nitrogen to produce 36 grams of ammonia. I have enough hydrogen to produce 67.6 grams of ammonia. How much ammonia can I actually produce then? The lesser of the 2 amounts. That's the amount I can actually produce. That's the most I can produce in theory. It doesn't matter that I have enough wheels here to produce 68 cars if I only have enough doors to produce 36. You can only produce the lesser amount. So this is my theoretical yield. It's the most I can produce in theory. It's the lesser of the two amounts. It's the most I have the chemicals to produce. What limits my production? Whatever reactant produces this lesser amount. So in other words, this 30 grams of nitrogen is my limiting reagent. So my theoretical yield is 36.5 grams of ammonia, and my limiting reagent is my 30 grams of nitrogen. So that leaves us with our last question: what's our percent yield? All right, so we know our theoretical yield, the most we can make in theory, is 36.5 grams of ammonia. Now to figure out our percent yield, we're going to take our actual yield, divide it by our theoretical yield, and multiply by 100. So now we have to locate that actual yield. Remember that number I told you to forget about it? It is forgotten no more. It may return to the realm of acceptable numbers once again. So we can now remember the existence of that 18.2 grams of ammonia that I actually produced in the laboratory. So when I performed the experiment, I produced 18.2 grams. I should have been able to produce 36.5 grams. I multiply by 100, and I get 18.2 divided by 36.5 times 100. And that gives me 49.9%. Ooh, failing grade. Except I got it very, very pure. That's where all my product went. I was concentrating so much on purity, I throw a whole bunch away to make sure it was pure. That's my story, and I'm sticking to it. All right, another example time. I have the reaction of magnesium solid and hydrochloric acid to produce hydrogen gas and magnesium chloride. How many grams of hydrogen can I produce from 30 grams of magnesium and 30, whoops, I should have grams there, shouldn't I? Grams of hydrochloric acid. Why don't you pause me and try to work this yourself? Did you pause me? You didn't pause me. I'm hurt. No, actually, I'm not. The fact that you can't even go a second without hearing me, I appreciate. I owe it all to my fans. But at any rate, once again, we have two quantities of reactant, correct? And whenever we have two quantities of reactant, what we're going to have to do is we're going to have to ask ourselves those two questions again. How much hydrogen can I produce with 30 grams of magnesium? How much hydrogen can I produce with 30 grams of hydrochloric acid? Alright, so now I just set it up like a normal stoichiometry question. I have 30 grams of magnesium. I'm going to place grams of magnesium where they'll cancel out. For my periodic chart, I always know that 1 mole of magnesium has a mass of 24.3 1 grams. I don't want moles of magnesium, so now I've gotten rid of grams of magnesium. I don't want grams of magnesium, so I'm going to place, I don't have moles of magnesium, it's getting late. So I place moles of magnesium where they cancel out. According to my chemical equation, for every 1 mole of magnesium, I can produce 1 mole of hydrogen. I don't want moles of hydrogen, so I'm going to cancel them out. I want grams of hydrogen, and according to my periodic table, there are 2.016 grams of hydrogen and 1 mole of hydrogen. I have the units I'm looking for, so I'm going to multiply everything on top, divide through by everything on the bottom, and I get 2.49 grams of hydrogen is how much I can produce with 30 grams of magnesium. Now let's try it again. This time starting with my 30 grams of hydrochloric acid. I need a new color. There we go. Okay. 30 grams of hydrochloric acid. I don't want grams of hydrochloric acid. And then, so let's see, I've got 1.008 plus 35.4527. 1 mole of hydrochloric acid is 36.46 grams of hydrochloric acid. So I've gotten rid of my grams of hydrochloric acid. I have moles of hydrochloric acid. Place them where they cancel out. According to my chemical equation, I need 2 moles of hydrochloric acid for every 1 mole of hydrogen gas. Gotten rid of moles of hydrochloric acid. I have moles of hydrogen. Do I want moles of hydrogen? No! No, I do not, good sir. So I get rid of hydrogen, and I know that 1 mole of hydrogen gas has a mass of 2.016 grams of hydrogen. Multiply everything on top, divide through by everything on the bottom, and I get 30 divided by 36.46. Apparently I'm entering the Olympic event of speed talking here as I race through these calculations at blinding speed. And I get... And I get 0.829 grams of hydrogen. So, I have enough wheels to make 2.5 cars. I have enough doors to make 8.8 cars. How many cars can I make? The lesser amount. So the amount I can actually make, and the answer to my question, would be 0.829 grams of hydrogen. That would also be referred to as my theoretical yield. Whatever produced my theoretical yield is my limiting reagent. In this case, it's my hydrochloric acid that limited my production. So my hydrochloric acid would be my limiting reagent. Because it produced the lesser amount. So there's another example. Another thing, quick thing about this example, is if we look at this problem, and for some reason this causes people confusion, and it's understandable. If you look at this equation, I had 2 products here, right? I had hydrogen and I had magnesium chloride. Did this question ask anything about magnesium chloride? No, it didn't. So do we need to do anything with magnesium chloride? No, we don't. A common mistake people make on exams is they think, oh, I've got that second product there. I need to wedge it into this equation somehow. And you really don't. The question doesn't ask for it, so you don't need to do anything with it. You can just ignore it. take a look at another example. A student reduces 3 kilograms of iron 3 oxide and gets 1.85 kilograms of iron. What is the percent yield? Now this question is really actually easier than most of the other questions we've done. It's just for some reason I've discovered through questions of the students that phrasing a question like this causes a little bit of concern. The first question that they usually ask is, well, I don't know what my numbers are. Let's take a look. A student reduces 3 kilograms of iron. So they've given me a quantity of a reactant. Then they tell me that the student gets 1.85 kilograms of iron. The student gets. That verb is implying, along with the fact that they've given me the amount of a product, that this is something produced in the laboratory. And therefore this 1.85 kilograms of iron is going to be a actual yield. That means we want to set it aside. We don't want to do any work with that number until the last step of our problem when it comes to determining our percent yield. So that means we're going to be starting with our 3 kilograms of iron. But what should we do with it? Well, if I'm wanting to solve for percent yield, I need to know what my theoretical yield is. So what I'm going to do is I'm going to solve for my theoretical yield. Notice, in this problem, we are assuming an excess amount of carbon monoxide, and we don't care about carbon dioxide. So again, don't force things that aren't in the problem. Neither of those is mentioned in the problem, and therefore for this particular problem, we don't care about them. Right? We're the ultimate cynics as chemists. We only care about things that can do us some good. Alright, so I've got kilograms of iron 3 oxide. So the first thing I'm going to do is I'm going to get rid of those kilograms. And I'm going to say, whoops, wrong tool there. I'm going to say 1 kilogram is 1,000 grams. So now I've gotten rid of kilograms and I have units of grams of iron 3 oxide. Now I don't want grams of iron 3 oxide, so I'm going to place grams of iron 3 oxide where they'll cancel out. I know always the relationship between moles and grams. According to my periodic table, 1 mole of iron 3 oxide has a mass of, well, I've got to go to the periodic table. Breaking news, the periodic table apparently contains molar masses. If we multiply 2 times 55.845, then we add 3 times 15.9994, we wind up with 159.688 grams. I have gotten rid of grams of iron 3 oxide, and I have moles of iron 3 oxide. I don't want moles of iron 3 oxide. I'm interested in moles of iron. According to my chemical equation, for every 1 mole of iron 3 oxide I can produce 2 moles of iron. I'm not interested in moles of iron, however. I'm interested in kilograms of iron. I know that 1 mole of iron has a mass of 55.845 grams of iron. So I multiply everything on, whoops, one last step here. I got ahead of myself. Because I don't want grams. I want kilograms. So 1,000 grams in 1 kilogram there. And I've gone to moles of iron, and then from moles of iron to grams of iron, and then last I'm going to kilograms of iron. So I multiply everything on top, divide through by everything on the bottom. And that gives me 2.10 kilograms of iron as my theoretical yield, as in the amount I should have produced if I'd had proper lab technique and done my work really well. So now the problem, blow it back up again here, is asking for percent yield. The problem's asking for percent yield, and remember, percent yield is actual yield divided by theoretical yield. So we can blow up our problem again. And remember that number, our actual yield, we said to forget about? Well, now we can remember it again. So we have percent yield equals actual yield divided by theoretical yield times 100, and that means my percent yield is 1.85 divided by 2.110 times 100 times 1.85 times 100 equals 88.2%. Ta-da! So the percent yield would be 88.2%. Why don't you write down Anansi, boys? Write down Anansi, boys. A-N-A-N-S-I. A-N-A-N-S-I. Anansi, boys. Really another good book. I enjoyed it thoroughly. All right. Call me crazy, but you may be done here. If you're in my general organic introduction, if you're in my introduction to general chemistry, 140, then you stop here. If you're in my college chemistry class, 170, continue forward for one more example. All right, one last spin of the dial. One last mystery involving limiting reagents and percent yields to get you excited for your homework. If I react 42 grams of carbon monoxide and 24 grams of iron 3 oxide, how much of what reactant do I have left over? Couple things about this question that make it unique. First of all, they're not asking about the products at the moment. They're simply asking about the reactants. They want to know what amount of reactant I'm going to have left over. So for the first time, I think in a long time, when we work a problem, we don't care about the reactants. What I'm going to do is I'm going to determine who our limiting reagent is and how much of the other one I have left over. And I'm going to do that by asking myself two questions. I'm going to ask myself, how much iron 3 oxide do I need to react completely with (42 grams of carbon monoxide? Then I'm going to ask myself a similar question of how much carbon monoxide to react completely with 24 grams of iron 3 oxide. So we answer our two questions working a stoichiometry problem problem each time. For my first one, I start off with 42 grams of carbon monoxide. I know that 1 mole of carbon monoxide has a mass of 15.9994 plus 12.011, 28.010 grams of carbon monoxide. So I've gotten rid of grams of carbon monoxide, and I know my next step is going to involve getting rid of moles of carbon monoxide. According to my chemical equation, 3 moles of carbon monoxide are required to react with 1 mole of iron 3 oxide. And I know that 1 mole of iron 3 oxide has a mass of 55.847 times 2 plus 3 times 15.9994, 159.692 grams iron 3 oxide. So I multiply everything on top, divide through everything on the bottom, and I get $79 grams. So if I'm to react 42 grams of carbon monoxide with iron 3 oxide, I need 79.8 grams of iron 3 oxide. Do I have 79.8 grams of iron 3 oxide? Do I have that much iron 3 oxide? No, I don't. So what does that mean? That means that my iron 3 oxide is going to limit my production. That iron 3 oxide is my limiting reagent. Because I don't have enough iron to completely consume my carbon monoxide. I'm going to have extra carbon monoxide left over. If you're not seeing that, then let's answer this other question. The answer to this other question will make it doubly clear. How much carbon monoxide do I need to react completely with 24 grams of iron 3 oxide? Well, I have 24 grams of iron 3 oxide. I know that 1 mole of iron 3 oxide has a mass of 159.692 grams of iron 3 oxide. According to my chemical equation, for every 1 mole of iron 3 oxide I need 3 moles of carbon monoxide to react with it. I don't want moles of carbon monoxide. I want grams of carbon monoxide, and according to my periodic table, 1 mole of carbon monoxide has a mass of 28.010 grams of carbon monoxide. So I punch all that into my calculator, and I get, drum roll please. Seriously, do you have a drum? Anybody have a drum? I really need a drum roll that's like pre-recorded so I can drop it in here. Divide by 159.692 times 3 times 28.010. Did I beat you to it? Is my calculator faster than your calculator? And I got 12.6 grams of carbon monoxide. So to completely consume my 24 grams of iron 3 oxide, I need 12.6 grams of carbon monoxide. Do I have 12.6 grams of carbon monoxide? Yeah, I do. I actually have 42 grams of it. So I have enough carbon monoxide to completely use up my iron 3 oxide. Therefore, my iron 3 oxide is my limiting reagent. Another way to think about this here. Whoops. Trying to shrink things down a little bit here. Another way to think about this is all right, that puts into words what I was talking about. Do I have enough carbon monoxide to completely react with 24 grams of iron 3 oxide? Yeah, I do. I only need 12.6 grams, but I actually have 42. That means that my 24 grams of iron 3 oxide is my limiting reagent, and that I'm going to have excess carbon monoxide. How much excess? Well, according to my calculations, I only need 12.6 grams. I have 42 grams. So how much am I going to have excess? I'm going to have 29.4 grams left over after I react all my iron 3 oxide, because my iron 3 oxide only needs to use 12.6 of it to be completely consumed. So my answer to the question in the long drawn out explanation there is that I would need 29.4 grams of carbon monoxide. That's it. That's all there is. Beep.